Welcome everyone. This week we're going to be doing things a little bit different. Instead of the live action class they wanted you to have, we're going to do it this way. Basically what we're going over today is most of your classes should all have team assignments by now. There are a few other things that we're going to cover, but this is going to be for the rest of the semester. We're working on primarily this project because we want you guys to really be thinking through the design process. We want you to be prototyping early and often, trying to figure out clearances and tolerances and all of those sorts of things. So what is this project? This is a traditional Japanese racing series. Tamiya is a manufacturer that does a lot of RC car, model cars, all of those sorts of things. So this is something that started in the kind of early 80s with realistic models, and then they, as many things Japanese do, sort of evolved over time, involved racing, more cool sponsorship stickers and anime series and all of those sorts of things. So the idea is they kept developing these mini four-wheel drive cars, and they're trying to figure out how to minimize the friction and how to use hop-up parts, or grade-up parts. Very Japanese way of phrasing things, because you want to make things as light as possible, as bright and colorful as possible, to make it fun for the kids. That's literally why all of this happened. So probably this four-wheel drive series is responsible for much of the Japanese cartooning scene as we understand it. So this is actually where all of that stuff begins, and everybody else that tells you otherwise is probably just trying to sell you something. So they do have several different variations of motors. We only have a couple on hand on campus that I'm aware of. We tried to get ones that are a little higher torque. We'll look at some of the kind of broad principles here. But one of the main things that you want to keep in mind is some of them are set up for top speed, some of them are set up for acceleration. So everything in engineering is a compromise. These are in fact no different. So these gear ratios, starting around like 4:1 to 5:1, the higher the gear ratio, the more torque being applied. So I went for a 4:1 or even less. I forget what my actual ratio is. Mine might even be closer to a 3:1 in the chassis design that I used this last time. The motor had to work way too hard, drew tons of current, and wrecked the batteries. It just couldn't hack it. So I would need to do a redesign on the motor and chassis in order to shrink things down a bit to get things cooperating. So I tried a very different design, and that turned out to bite me pretty hard. So the 4.2 to 1 ratio is better. 5:1 ratio is a little bit better still. You guys are welcome to do a little bit more research here. There's tons and tons of YouTube videos. Some of them are in Japanese and filmed in almost like game show style. There's tons of resources out there. We have kind of a fixed tire size for kits. Most of those should be available for you guys to start taking measurements for in the classroom once everybody's back from break. There are also going to be some differences in terms of how the car performs, a narrow car versus a wide car. In our case, it's kind of difficult to package everything with the way that we're doing this. With a narrow car design, it can be done, but it's recommended that you kind of take advantage of the space that you have, but not so much so that you try and make the car body as wide as the track because of reasons that we'll discover here shortly. So narrow arrangement is often fairly good for longer straights, but the wide tires are are better in terms of some of the braking and performance grip. In the design that I've shared with classes, I went with a wider tire setup, which in practice for me made absolutely no difference. They talk about different things like the tire materials. We have rubber tires for class use. They work pretty well for this. They have pretty good grip, so there's really nothing wrong with those. We don't have any of the sponge type or the Reston type, so you don't have to really worry about those. So tire maintenance, I mean, wiping them off, at least make sure they're okay. You don't need to do anything crazy with them. The wheels are different, but in a lot of cases what they're really doing is they're changing the look of your car. I don't recommend 3D printing your own wheels if you're just really interested and you just really hate the wheel design. You can just keep in mind that it's pretty tricky to get the wheels completely centered so that you don't have so that you actually get even rotation and you don't end up with a circumstance where the tire is sometimes making contact and then lifts off the track depending on where it is in the rotational cycle. So there are a lot of considerations there. For the most part, we use a standard narrow wheel configuration with rubber tires, so fairly low coefficient of rolling friction overall. Another really big consideration, this we don't really spend a lot of time worrying about because we're not designing the cars with differentials and all kinds of crazy technical stuff, because that just adds weight, difficulty, complexity, and sets you up for failure. You want to go for as simple as possible for a lot of reasons. So rollers are something that we don't emphasize very heavily in terms of the chassis design. What rollers are going to do is help keep the car off of the walls. If you don't have rollers designed in, it tends to have the wheels or the body scraping against the sidewalls. That slows you way down and can help burn through your battery in just a couple laps. So you really want to design the body to be narrower than the overall width available. That way you can kind of keep the design retained inside the walls. So they have a few different kinds of strategies. There are some different strategies in terms of tuning the rollers. Some of them, if you're keeping it kind of even and you try and keep the wheel contact about the same, that's going to be a pretty good balance. The larger in front tends to work well if there's lots and lots of corners, which our track has a lot more corners than not. So there's a lot of turning, there's a lot of direction changing. So ours would be one where you might consider different roller sizes, but keep in mind each of these has a cost trade. So going to TamiyaUSA.com about Mini 4-wheel drive will get you some information. You'll find the same link searching for Tamiya Mini 4-wheel drive, and this will get you kind of some things to be thinking about for each of your teams. The roller position also matters. For the most part, we don't tend to need the front, side, and rear rollers because we're not getting upwards of the top speeds of these courses typically with these designs. So a simple 4-roller design front and rear is probably optimum for what we're doing, but you guys have the options of kind of changing stuff around. You can customize the position of those. The narrow setup is kind of has an advantage through the sharper curves. Sort of the wide rollers in this case. So the wider arrangement of the rollers is less movement side to side and a little bit more controlled, but you don't want to design it to be full width and really contacting both walls. So you kind of want to split the difference between these two so that there's not a lot of side to side movement, so that your car isn't trying to drive at an angle and spending a bunch of its energy pushing against the wall, because that's just going to slow your car down and create some headaches. Low positions are okay, except for when you get to higher speed corners and things. The low really isn't suitable. So most of the time I encourage students to design like mid or high position, because there's going to be enough issues trying to reach top speed that like the mid position is really pretty optimum for most things in these designs. So your teams are going to be designing several components. You're going to design the chassis. You're going to be given a motor, gears, the control board that we designed. You're going to be given the axles. I'm going to work on putting up drawings for the gear sets, but we'll look through some of their tech tips here to get some ideas of what can be done. So these tech tips, what they're working on is trying to give you a sense of what's allowed in different classes. We're really not paying attention to those details. I can tell you that some of the gears that we have are either blue or yellow 23 tooth. We have some of these purple 8-tooth pinion gears that go on the motors, so you can do some math there. The ratio of 8 to 23 gives you a sense of what the ratio looks like. So 8 to 23 is or 23 over 8 here is a 2.87 ratio. So I had one that is I have one of the pink spur gears that I want to say is, let me see if it still has the number on it. I think it does. But I don't see it printed on, so usually the gears will be printed on the surface. I don't happen to see it on this one. I want to say the pink gear, I'll see if I can find it elsewhere in one of the kits. It's not a 22 tooth. I want to say it's I really want to say it's like this 13 tooth. But 13 is not quite correct. So a 13 tooth to pink to yellow is what I was trying to use, which is on the order of like a 3.7 or so. So here, typically what you're doing is you're reducing this a couple of times, so 23 to 8, and then you're doing another reduction because something like these spur gears often have an inner gear. So the yellows or the blues that we have tend to have I want to say that's like the 13 tooth inner gear, because it's not the same design. It's not the crown design. It is still, it's more of a counter gear design. So the blue that we have is a little different. So you can't use all of these same spec sheets. I'll try and show you guys what combinations we have, but it's trying to give you some kind of an idea what the gearing will do. And so what you want is really good acceleration. And this was the issue that I was having, is at these lower ratios, the acceleration means the motor is working way too hard for my particular chassis design. So instead, going for a higher gear ratio, even as high as 5-to-1, is going to be the best acceleration. Don't be concerned with top speed. You want to be concerned with completing laps, where the torque gearing, the higher ratios, is going to be a whole lot more useful than trying to go for one of these lower top speed ratios, because climbing, which it has to do in our course, and accelerating, which it has to do in our course, the lower ratios just don't work out well. So you want to stick to a higher ratio, somewhere over 4 as your final ratio, because of a lot of reasons. Motors, a lot of the ones that we have, I want to say, are like the Hyper Dash 2. I think that's the red one, and we have I think we have some Hyper Dash Pros, and you can see there really aren't a lot of differences in the specs. The Hyper Dash Pro maybe could take more current, but a lot of times you're not going to hit these top end numbers. So I even played around with a Plasma Dash, which is supposed to be the all-out baddest, most gnarly motor, highest current draw, which is why I was melting down batteries. And this one really works well as a motor. The problem is it just can't produce the torque needed. So none of these are going to produce really high torque. They're really all in the same range. There are some super secret Japanese break-in processes that people use with different special oils and things. We haven't done any of those things. We also did not sit down and have traditional Japanese tea when we were putting them together in the kits, so that was a mistake, I'm sure. That could have really improved our overall performance. So the kinds of things we have are some of these lane changers. We don't really have slopes as much, but we have some lane changers and corners. And so we end up kind of with tracks more like this, where you have a crossover section, you have a looping figure of some kind. So lots of corners, lots of lane changes. We have at least a pair of those. So lots of things going on. Ours is not 3 wide, it's 2 wide, but the same kind of idea as this. So this is kind of more what you have to mentally plan for when you're working through these designs. And that kind of dovetails into some of the next things that we're talking about here. So there are a bunch of different kinds of wikis out there and things. There's a bunch of different kinds of pages telling the stories in very anime style of a bunch of these different cars and their drivers and all their character history. And so if you thought it was just about the cars, then you're sorely mistaken. I mean, who doesn't want early 90s Honda City turbo car? I mean, I certainly would not want to drive one on American streets, but they did make a bunch of cool sort of total body designs for a bunch of these different special racing cars, some of the most famous being some like the Rayburg or the Calsonic GTR. This is probably the single most famous of the car full body models that they did. So if you really want Japanese speed secrets, look no further than Gojira, because this is one of the most important racing cars in their racing history. So most things Japanese, you want to make yellow in order to make them super duper fast. That's why the yellow Type R's were so rare back in the day. But if you want to go really fast, then a GTR that's it. That's sort of the cream of the crop. All the super kitties just got really super mad, and that's okay. There's a bunch of cool stuff that they've done with different designs, but a lot of the chassis, regardless of what type of body they put on it, a lot of the chassis are sort of similar. So I think even some of these variations from the Formula One era cars, a lot of them all have similarities. So you'll see a lot of, especially the more modern ones, you'll see rollers designed. Some of the original ones, like the Clodbuster, these weren't fast enough at that point in time for their designs to need those things. That was not really a thought process. So this really expanded very, very far beyond what the original scope was, which was just to make some cool stuff. So as with everything, there's rules and regulations. So what we have to do is fit within these constraints. So 105 millimeters is approximately the width of the total track. The length has to be under 165 millimeters, including rollers and all the other dimensions. Some students have made the mistake of making bigger vehicles and treating this as a shoebox size and trying to fill the shoebox with the body of the vehicle. They ended up with a car that worked and could have completed a lap, except they made the body longer and full spec width, and then it got stuck in the corner. So you really want to stay under this 165 millimeter total length for a lot of reasons. The height under 70 millimeters, including, all of your wings, self-defense mechanisms, knives, guns, and bombs. So you want to keep that in mind. You also want at minimum a 1 millimeter surface clearance. I might recommend shooting for closer to 1.5 millimeters or so. But you want to make sure that you're not having the chassis sit all the way down on the ground, especially if you have gears protruding through the bottom. You're going to create all kinds of issues for yourself. Keep in mind that the drive gears in the chassis have to have the gear going through the center of the shaft. So you're going to have to account for some of those heights in your design. The tire diameter, we've set, tire width we've set, so you don't have to worry about those. We're using one of the narrower tire setups. The weight needs to be on the order of 90 grams. In this particular spec, we're less focused on the 90 grams part. It's naturally going to be very easy to hit 90 grams with these designs. You can technically have unlimited amount and type of rollers. If you want huge silver dollar size rollers, go for it. If you want a couple smaller size and more distributed, that's great. Gears, we're not as picky about setting gear ratios. We just want you to be mindful of what can be done with the gears that we have available. So I'll pull up an example of the gear kit and show you what I'm talking about in terms of how those look. So we'll see some examples and some of the pictures that I'll share to give you some ideas on what your teams might be able to do. So you guys are going to have to meet and start sending messages back and forth in the forum about who's going to be working on what parts. We have to draw the axles, the wheels, the tires. We have to design the chassis and the layout and try and account for the spacing between the gears and all sorts of things. So they give a bunch of clear examples and details here, but we really want to pay attention to kind of the chassis layout. So here's a really good, simple example of the chassis layout, and I'll try and make this as big as reasonably possible with maximum pixelation. to cause all of those 4K gaming kiddies anxiety. All right. Many designs have something sort of like this for good reason. Battery on one side, battery on the other side, motor in the center. A lot of ours are double drive type motors. So you saw that in the example here. I think the motor they used was, so a Japan Cup, so a Hyper Dash Pro. So we have some Hyper Dash Pros as well. They're double drive motors, meaning the shaft extends to both sides. In the case of one of the motors that I tried, the Plasma Dash, that's a single-sided drive. But most of these are all double-sided drive. So what that means is you can put a drive gear on either side of the motor and not try and run both axles off of the single side of the motor. That turns out to have advantages in terms of overall gear drag and some other things. So you want to pay attention to those little details. In our case, chassis need to be modified slightly from this design idea because it's not practical for us to solder leads to batteries and things in order to make this kind of design work. We tend to have battery boxes that connect. So 2 AA battery box is probably what you can expect for most things. And what that means is you need to account for the space. So you can still do something like this and put the battery box sideways on one side or another. You'll find that lengthwise, in order to get the packaging to work, you really can't fit easily the battery between the two wheels. You kind of need it to be inboard of the two wheels, so it has some limitations. There are also circumstances where students have taken this and turned it sideways and put the motor up front or in the rear to try and do like a mid-engine type design, or try and do a front engine type design with all-wheel. Any of them can work so long as you're keeping track of how you're running the gears, and keeping in mind that when you rotate the first gear one direction, the gear next to it has to rotate the opposite direction. So you have a reversal, and you have to keep that in mind in terms of your overall chassis design. So what you'll see is these two gears. You'll see the first gear on the motor. You'll see a driven gear. Then you'll see another gear down to get to the axle itself. So there's a couple different steps typically for this. So this one would be some kind of a crown gear with a spur gear, and we'll take a look at what some of those look like in the drawing sets and diagrams, and you'll see, based on the different types of gears that we use, what you might expect from each of these designs. You want to have some sort of roller design. I find that for practical purposes, front and or rear rollers suffice for most things, so long as you're keeping within the width. This is showing you where different roller guards might go. So long as you have the basic rollers, you really don't need these additional guards, because we're not achieving top speeds. These are mostly to protect the tires from making wall contact at much higher speed, but we don't have to worry as much about those. So these are injection molded chassis, but you're going to be 3D printing your own design. Alternative methods have been taking this same sort of transverse mounting mechanism and then running it, or I guess this is a horizontal mounting mechanism, and mounting it to one side. So you're still driving these gears, you just move everything to one side and then leave you more room for the battery pack on the other half of the chassis. So that layout tends to work pretty well and give you the clearance that you need for the battery box. And then you can get things laid out pretty nicely. But each of these gears has to go into a housing. So there's another chassis design that I can show you that I'll pull up from that'll pull up in SolidWorks to go over as far as what some of the mechanics are, because I think I have an older version of the instructor car chassis. So you want to keep in mind some of those factors. We have a predefined set of motors. I think we only have 2 or 3 different total part numbers. I'm not sure how much they're going to be changing this semester. We'll see. Parts availability could be an issue. So you want to make sure that you have a completely assembled car. Let's take a look at a few examples. Early on, our track looked like this. Now we have a much more detailed track with many more turns, many more of these exchanges. So you're going to be going around the circuit. You're going to be going up and over these transitions. So it goes left to right, right to left, up and over. There's a lot going on with these particular designs. There are a lot of different kinds of chassis designs. So here is a view of a pair of them. So I think they had a few specialty ones. This was like very, very, very first run of this overall. This is some sort of battery box. We don't have anything like this for current runs, but you can see some kind of a roller design on the chassis, some kind of chassis to set up the spacing of things. And then additionally, you have the chassis designs where you have, in this case, they had springs and like a proper roller kit. So they had a few different kinds of accessories. You can see some of these pink gears and some of these spur gears, and then these little purple gears. We'll look at a couple other examples. So this was a design where this is sort of the pile of parts design. Here, I think they were trying to set up the motor in the center and drive this gear directly from the motor, which you can do, but if you don't have proper gear mesh there, then no amount of tape is going to help you. So they tried to wire the motor directly in. We didn't have the control boards at this time, so lots of little technical issues. And these original series wheels that we have are long since gone. Some other designs that sort of start to make a little bit more sense and look more like what we recommend at this point are this. Now, this particular one is not four-wheel drive. There are points assessed for whether or not the car has 4 driving wheels, so you want to keep that in mind. If your team decides those points aren't worthwhile because of the complication, just know that you have limits on how effective that will be. So here's another 2 different kinds of gears that you can see. So our blue gears have the spur gear, but they also have the counter gear. So these are typically classified as a counter gear. This has a nut that sits in this recess and attaches to the axle to give a positive lock so that the axle can rotate when this gear is turned. So all of the outer tooth count is 23, except for, I think, our crown gear is 21 teeth. The yellow crown gear, I'm pretty sure, is 21. And I think this interior is all 13 tooth. I'm pretty sure on both of them. So the 23 to 13 gives you a further reduction of 1.7. So they tend to they tend to help to have a couple of these in line, so you're multiplying the torque and cutting the speed of rotation by a fraction, but giving yourself a higher chance of completing a lap. So those designs, while they can work, they tend to really struggle for a lot of reasons. So it's helpful to use. That's a little better view of it. So here they used a very large driven gear and a smaller or a very large drive gear, very small driven gear. So that means that the motor rotates a lot for every time that the axle rotates. So this would complete a lap very likely, but it's geared in such a way that the motor's spinning a lot, the axles really aren't. And so that ratio is more torque oriented, and so this would complete a lap, just do so a little bit slower. Let's look at another design. So similarly, this one, I think they had 3D printed the posts. Yeah, they had 3D printed the posts for their design, and it sort of can work, but if you 3D print posts instead of relying on using hardware like screws, you've got to be really careful about the strength of things, because a 2mm post looks fine in SolidWorks, but when it's 3D printed, that's extremely fragile. So you want to keep that in mind in your designs. So you're noticing kind of a common theme. This is more the layout that I'm referring to. So this one obviously did not reach quite completion. But we have the purple gears, you have that driving a crown gear, and then you have further reduction from the counter gear down to the spur gear running the actual axle. So this was a good attempt at this, but it's really hard to get this gear spacing correct. But the idea behind this chassis design is pretty sound. So you want to be thinking in terms of this and how this could work. So more commonly, we would have the crown gear, and then we have a smaller, like 13 tooth counter gear, and then the 23 tooth gear again on the axle is more typical for the ratios that we would set. So let's look at another example. This one I think was one of the narrow front wheel options. So this one just sort of has a motor up here, and so really only the front wheels drive, and that's a definite maybe for this one. Let's look at another design. So this one looks cool, looks pretty complete. Can't really see from this angle. I think the person taking that picture had way too much coffee. This is better. But this particular wheel is coming off that axle, so they should get that looked at. So this design, trying to run just the gear with the so the 8 tooth with the, I think these are like 19 tooth or so crown gears. So this is what they were trying to do with this. Oftentimes you find that your spacing turned out to be not quite correct to get the wrong gear lash, but they're also short a AA here, so I don't know if this completed a lap or not. There were some other designs, but I think that covers most of them. This is one of the other ones. Let's take a look at this one. So yeah, this was similar kind of idea. You can see that the motor is canted sideways in order to get the engagement. That's really bad for gear lash engagement. So this one might have run, but without its rollers, it broke a couple of the front posts, looks like. Without the rollers, this would be very hard to get it to complete a run. So it's just things that you want to be keeping in mind. I think that covers all of the designs that I've got here. Yeah, there's a couple video runs and things, but anyway, it gives you some design ideas, and I'll take a look at what designs I still have, because I think I had some in SolidWorks. Let me see if I've got the instructor car chassis, which I should. I may have it in a newer folder. Might have been fall 21. Maybe not. So I'll take a look for this and pull up SolidWorks and see what info I'm missing. Yeah, I think it's in... I don't think I have it there. It might be in 20. So I'll try and find the instructor chassis. I'll pause this here and come back when I've located that. So here we have an example of half the frame. Half the frame that the motor sits into. So the motor comes here on this side and sits. I'll have to do an assembly maybe if I can to show you an example of what I'm referring to. Then we have one gear sits here, one gear sits here on two shafts. The center of this gearbox is here. So that was the mate to one side. Motor sits here. Drive gear, driven gear that drives the axles. So pretty straightforward arrangement. I'll get drawings set up with some more detail about how these work. These gears are 34. So the ring gears are actually 34 and 12 teeth inside. So 34 and 12. And our counter gears are 36 and 12. So 36 outer teeth, 12 inner teeth. You can see they have not exactly just a straight point. They are rounded in the end. They do come to a V shape inside, but this will give you an idea of how these are done. There are slight chamfers on either face of the gears. So there's a lot of detail here. I'll try and get as much of that captured in the drawing as possible. So then we have a 36 tooth lock nut gear and the 36 tooth lock nut gear. What that does is clamp onto the axle using the locking nut. So this has a hole in it that's threaded for it's threaded for a set screw that'll lock onto the smooth round axle and help keep that gear fixed, so that this gear actually ends up being what drives the axle. So interaction with this gear is what actually drives the car down the track. So I'm going to put together drawings for you guys so that you can get some key detail, since you won't be able to necessarily measure all of these parts. I'm not going to be focused on the minor details such as the exact chamfers and things. I'm focused more on the overall diameter, as well as the tooth count being correct, the thickness being correct, so that you guys can get the correct center to center distance for each of these. So those drawings should really help clarify what you guys are making. So I'll try and include several views and make sure they're really clear on what it is that you guys are building, because it's really important to get the depths and things right. And I don't think in my drawing package here, I don't think I've got the 8-tooth spur gear, but it's going to be the same kind of pattern, the same kind of process, but it's a smaller diameter shaft, so I will try and get that detail as well. So this should about wrap it up for some of the things that you need. We'll discuss more in class this next week as you guys are starting to work on these. So if you have questions, I will try to keep an eye on the forum, but don't expect a lot of reply necessarily this week. I'll do what I can. So hopefully that'll give you guys some guidelines on what to be looking for, how to be divvying up the work, and so on.